How fast is human brain? What is faster, a brain or a computer? Or maybe let me ask you even more simple question. How fast is one neuron inside our brain? How frequently does it fire? And I ask this question quite often, and usually people answer something like a few million times a second, 100,000 times a second. Sometimes they would offer more modest estimate, 1,000 times a second, 100 times. But very rarely someone gives correct answer, which is, on average, a human neuron fires once about every 6-7 seconds. So apparently, neurons are quite slow. Our brains are quite slow. If we compare human cortex with the most advanced server available on the market right now, this kind of server is going to cost you about $500,000. There are 8 top-of-the-line NVIDIA GPUs attached to it. The server is going to be about 1,000 times faster than a human cortex, faster in terms of number of operations per second. The human brain, however, has more memory, about 20 times more memory. And of course, it's way more efficient in terms of energy consumption, but that's not the point of the discussion today. The point is somehow the brain is still way more efficient comparing to a server. We're talking about just one server, even though very advanced. Yet the server is 1,000 times faster. So can we learn something from the nature? Somehow nature figured out how to replace this expensive compute with cheap storage, how to trade compute for storage. Maybe we can do the same. And basically, this is the first of 2 foundational ideas of Pythagoras, trading compute, expensive and slow, for storage, fast and cheap. Compute once, reuse forever. Let's take a look at the demo. We are going to run the demo in the Google Colab. It's a Jupyter notebook in the cloud. Don't read all those explanations. You can read them later. The notebooks are available on GitHub. Right now, just look at the code, and I am installing Pythagoras. I am doing all the imports, and now I can create a portal. A portal is basically a shared storage. This is where we are going to cache all the intermediate results of all the computations in our programs, so later we can reuse them without a need to recompute. This example, a portal is just a local folder, but it can be, say, a Dropbox folder shared across hundreds of computers, or it can be an NFS folder shared across thousands or maybe tens of thousands of computers, or it can be an S3 bucket shared across millions of computers. But it's still just a storage. It's very cheap. It doesn't require any constantly running servers, any endpoints to connect. It's just a storage. Once we have a portal, we can use a pure decorator that comes from Pythagoras and apply it to our function. And once we do it, we can use this function, this piece of code, the same way we would use it before without Pythagoras. We just run it. And this function does some very advanced, expensive computation, runs for 5 seconds and produces some result, this magical number 22. The second time we run this expensive function, the result is instantly available. But of course, if we run the same function with a different combination of inputs, then it's going to execute from scratch. It's going to run for 5 seconds. The second time we attempt to execute this function, the result is going to be available instantly. But of course, in real life, source code changes all the time. And let's modify the last line of our function and see what happens. Let's call this function with the same inputs. Pythagoras understands that the source code has changed, so it re-executes the function. The second time we execute the second version of the function with the same combination of inputs, the result is available instantly. And if you go back to the original, to the previous version of the source code and call this updated version of the initial version of the function with the same inputs, of course, the results are available instantly. So Pythagoras tracks changes in the source code and caches different, caches all the execution results for all the versions of the source code that we used. And it's reasonably smart. For example, if we make some cosmetic changes to our source code, say we just add some docstring and some comments and modify formatting, but we don't change the actual substance of the code. When we try to execute this updated, modified version of the function with the same inputs, the results are available instantly. And of course, you can say, hey, this is a technique which has been known for decades. It's called memoization, caching the outputs of functions. Of course, it has been known for decades. But in the past, the cache was usually stored in RAM, which means you restart your program, you restart your computer, the cache disappears. In our case, we are talking about storing results persistently in a persistent, distributed, shared cache. So you compute your results today, but you can reuse them tomorrow, 10 days from today, a few years from today. And if you share your portal with other people, they will also benefit from using your cached results. And as you can see, as I said, it's just storage. It's just a folder in a local drive. It could be some other type of storage. And it shows that right now we cached execution results for 3 function calls. But on top of that, we cached many other things. Why? Because, as I said, we are trading compute for storage. We are storing basically everything which is storable, all the input values, all the source code, basically everything. So we can easily reuse it in the future across many different computers. And to some extent, this strategy is very similar to, say, social networks. The more people are using a social network, the larger the value each of them gets. The same here, the more programs connects to the same portal, the better the hit rate for the cache, the faster are those workflows which are accelerated through using Pythagoras. Of course, this technology doesn't make sense for real-time latency-sensitive workflows. It makes sense for expensive, resource-hungry, slow-running workflows that are taking minutes, hours, maybe days, or even weeks, or even months to execute. But apparently, that kind of workflows, they're a big deal. Last year in the United States, enterprise spent over $100 billion on those slow-running, resource-hungry, expensive workflows. And this is exactly where Pythagoras shines. So basically, that was the first idea, persistent memoization. Let's take a look at the second idea behind Pythagoras, which is reusing underutilized resources, underutilized hardware. Let me ask you a question again. On average, in an enterprise, what is a utilization rate for servers? And I assume many of you know the answer, because there were so many reports, dozens, maybe even over 100 reports published about it, and they all have reached the same conclusion, which is for non-tech enterprise, utilization rate is super low, it's below 20%. For tech enterprise, it's higher, especially for hyperscalers. It can reach 40%, maybe even 50%. But on average, still the utilization rate is very, very low. It's below 30%. Of course, it's very logical to try to use those servers for other workflows, for those slow-running workflows that, as we just discussed, they're very expensive. But it's not that easy to do, because there is a reason why people over-provision their servers. They over-provision for peak loads, and we don't know in advance when those peak loads are going to happen. And it's very hard to synchronize how do we run our expensive workflows, which are not the main purpose for the servers. How do we run those workflows of those servers without distracting them from their main job? What if that peak load happens exactly at the moment when we try to use them for some other purpose? It's hard to synchronize. Timing is important. But if we are applying the strategy that comes with Pythagoras, which is compute once, reuse forever, timing becomes less important. We can decouple the moment when we do computation from the moment when we need the outcome of that computation. We can proactively execute those workflows, and then when we need the results, they're already in the cache. this way it becomes way more easy to use those underutilized servers. And basically, we can triple the server fleet for an enterprise without extra investment into hardware. Let me show you how it works. Very similar example. We are installing Pythagoras. We are doing the imports, and we're creating a portal. And let's take a look. Let's take a look at the describe method that shows what is inside the portal. And when I told you that a portal is just a storage, it was half of the story. Yes, it's just a storage, and there could be millions of computers using this storage, using this portal. But each of those computers that are using the portal, in the background, they're launching a few background workers. And the more available resources a server has, the larger the number of workers it's going to launch. And we're only launching workers that are using underused resources. We are only using idle resources. And what happens when that background worker launches, it starts looking into portal, looking for an execution request. Maybe someone placed an execution request to launch some code. And if the worker finds this request, it lets all the other workers know, hey, I'm working on it, don't touch it. And it executes this. And then once it executes that piece of code, it puts the results into the cache. So the next time someone wants to execute that code, either synchronously or asynchronously, the result is going to be available instantly. Let's use the same example, the same expensive, smart, slow-running function. When we call this function in a synchronous mode, it runs for 5 seconds. But now let's try to call this function with a different combination of inputs using asynchronous mode, using the method called swarm. The way it works is going to put an execution request into a portal and immediately return the address for the future result. And after we do it, we can use a function called ready to check if the results are ready. Of course, they're not ready. We know that the function takes 5 seconds to execute, and we don't even know whether any of the workers actually started working on it. So, of course, it's not ready. But let's hope for the best. Let's call this method ready again. And yes, now the method returned true. So while we were talking, some of those background workers took care of this function. Now we can use a function called get to get those results. And the next time, if we call this function in a synchronous way, our expensive function, with the same inputs, the results will be available instantly because they are already cached. And if we look into the describe method, we can see that now we cached 2 execution results. One was a synchronous call, the other was asynchronous call. We still have 3 background workers, and at this point, the execution queue is empty, but it can actually have millions of execution requests. And the beauty of this approach is the more programs connect, the more nodes connect to the same portal, the larger is this virtual cluster of background workers. The larger is this swarming pool of workers looking to execute the code. The bigger is the larger is the performance of this virtual cluster. And there is no central scheduler. There is no central active backend that offers some endpoints to connect or that requires some servers to run. Basically, the more programs are using the portal, the larger is this swarming pool of workers which are contributed by each of the programs that is using the portal. And of course, in this example, we are using Google Colab, so it's basically a virtual machine in the cloud. It's just one machine. So we only have those 3 workers working in the background. But of course, in real life, we're talking about way larger clusters. Of course, not every node is capable to execute every code. Pythagoras offers this concept of prevalidators that allow workers to check whether this specific function can be executed on this node. For example, this prevalidator checks whether a specific package is installed on a local node. If it is installed, fine, a worker will execute the code. If not, first the worker is going to try to install this package. And if the installation is successful, then the code is going to be executed. Otherwise, the worker is going to give up, and then hopefully some other worker on some other node will execute this code. And we have many different prevalidators. For example, there is a prevalidator that checks what is the amount of available memory, unused memory on the node, and we can create a request pretty large amount of memory, and only a server capable of offering that amount of memory will be able to execute this code. And we can combine those prevalidators. For example, this prevalidator checks for two specific packages whether they installed, and also checks whether specific node has at least 10 unused CPU cores, etc., etc. You can think of very advanced prevalidators that are checking, for example, if you have some specific super powerful GPU on your server. And similarly to the previous example, the beauty here is the more computers are connecting to the same cluster, the larger, to the same portal, the larger is this virtual cluster, the bigger is the collective power of all those swarming workers. But however, if you don't have any computers connected to the cluster, to the portal, it's super cheap. It's just the storage. So basically, that concludes our demo. Let me know if this is something that is interesting to you. If you have any questions, I'm happy to answer your questions. Give it a try and try to integrate it into your workflows. I will be very interested to hear your feedback. Thank you, and looking forward to hear from you. See you.